Let's have a quick homework review, which is homework 925. So this problem asked to design a PID controller for a system G and then having PID controller. And then it gave us the design specification, so which is peak time is 1.2122 seconds, which is nothing but omega d pi over omega d. And then damping ratio, that's very nice. It's already gave damping ratio, not the overshot, is 0.07. So for due to time constraints, I just have all this homework already here. The solution is here. So the original plan is k over s plus 1 and s plus 3. And then we can draw the root locus for this. So if you are drawing root locus for this system, what you are drawing root locus, you are drawing root locus for, you have a P controller, and then you have something like this. So this is a root locus for simple P controller system. And then these are the trajectory or the root locus are the poles or solution of the closed loop transfer function. So the closed loop transfer function means that you can do block diagram reduction, which is for this block diagram, and then TS will be, let's say this is still G, 1 plus KG, KG, and the root locus are the roots of 1 plus kg equals 0. And then the k is a variable here. So each point corresponds to the solution of this equation, star equation for varying k. So these -1 and -3 are the solution when k equals 0. And then these 2 points can be a solution for k equals some value. Other roots, the point in this root locus are the roots of this star equation y varying k. You draw the root locus based on the rule you learned previously. And then there are 2 poles. So there will be 2 asymptotes, and then center is -2, which is here. And then theta A can be calculated by using this equation. Phi over number of poles, number of poles and the number of zeros. And this is the root locus for the P control. And then let's look at the design spec. The design spec is using this damping ratio and the peak time. you can calculate the natural frequency, means that you can calculate the real part, which is as here, zeta omega n plus omega dj. And then you know the zeta, and then you know the omega n, so you know this part. And then you know the omega d because the peak time was given. So omega d is nothing but, omega d is pi over Tp. And it turned out that the desired pole location should be negative 2.8 plus minus 2.8 J. And that can't be root locus. Here, the point is, let me use a little bit thick pin. So this is the sigma A, and then that point is near here. So it'll be about this position, which can't be the solution of this star equation because there's no point. Means that whatever you vary in K, this desired pole location or desired of this desired pole location to meet the design spec can't be a solution of these characteristic equations. So what we need to do is we need to design the controller. So this is a transient response. And then we can design root locus to minimize, to meet this transient response or by adding 0. So this is a method, one method to design a PD controller. So transient response means that PD controller. Almost. Another way, we have another way. If you have interest in, please come to my office hour. I also show another way. And so that is here. And this solution. So now you have a new controller. So now your controller will looks like plus minus K S plus Z for the PD controller. And then you have S plus 1, S plus 3, and something like this. And then let's say this is C, this is G, and then your closed transfer function is this. And then now you want to find the solution of 1 plus CG equals 0. You means that your CG should be negative 1. So means that the magnitude should be 1 when S equals S star. And angle CG S equals S star should be 180 degrees. And we can calculate this angle using geometry. So this is the method calculating angle using geometry. So this is the S star, and then there is a negative 1, and then negative 3, in the potential 0 position. And then you can calculate angle theta 2 using, so this is the open loop pole location. This is the desired pole location. So basically you can calculate arctangent theta. And then the same thing, you can calculate theta 1. This is the desired pole location. So you are calculating this. This A over B. So this will be the A, this will be B, and then this is A, and then this is B. So calculate the theta 1, and then similarly you can calculate theta Z. Now it will be A over B. It means that Z minus the desired pole location and then the imaginary part. And this, sum of these two poles and this theta Z should be 180 degrees. And to make this, Z should be this value. So you can find out the Z using angle criterion, which is nothing but angle CG. It should be the 180 degree. Then you can calculate the magnitude of this gain. So we don't know what the gain, what K can make the pole, desired pole location as a solution of this equation. Yet, so if the magnitude is not 1, it can't be the solution, right? It should be 1 to make the solution. So you can, so now you have a closed loop transfer function, which is this, and then already, and then you want to make this is 0, means that you want to make this is 1, and then you can calculate easily. So this should be 1 at this pole location, and then calculate K. And so the desired pole location is negative 2.8, and then K is relatively small. So I suspect that you can typically select very small. Well, let's before going even there here. So then the another requirement was 0 steady state error. Means that you need I controller. And then by simpling I can make root locus a lot different. And now you already found a good pole location, good controller to meet transient response. But if you have only I controller, the desired pole location, the PD controller will not work anymore. So instead, you can design a PI controller not to vary your root locus a lot. But now the K is small, and then the pole location is, the pole is like only 3. So maybe like this. So the PI controller may change system response a lot. So what we can do is that we need to simulate and verify the response. So let's say this is our controller so far, the PD controller was 1.26 plus 7. Yeah, it's about here. This is a PD controller part. And then you can have a PI controller, not to vary your root locus a lot. But this can change the stem response. So for the sake of time, already made this code already. And then in the beginning, let's have PI controller as 0.01 and then see what happens. Oops. Seems like I need to change. So let's share the screen for now. And yeah, I just said that I already made this script and then having PI controller. And then this is the system response of the PI controller. And then this is the system of root locus. The root locus was not changed a lot compared to simple PID controller because PI is close enough. But now what happened is that because the gain is small, means that now the integral part is dominant to reduce steady state error, and then the pole location is near zero, so therefore it's very slow. So this is what happened. So the blue line is original P controller, and then we were able to reduce, system response, like if you look at the rise time and the rise time a lot, was settling time using PID controller. But now this PID controller shows that it can be very slow. The settling time can be very slow, even though the steady state error can be very small. So this is typically due to the fact that the gain is small, something like this. So we can make the PI is even closer of the I controller by making 0 to be very, very small. Then this is what happens. So then now because it's almost canceled out, so therefore your PID controller even almost does not work. And another method you can do is that it's because the pole is at the origin, makes the system very slow. So this is, and then if your T controller part, so PI controller have S plus 0 and over S. And then depending on your S plus 0 part, your system can be faster. So if we change I part a little bit fast, you can get faster response and then having small steady state error. And it may slightly violate the desired pole location, but I think this is much better response than the original PI controller. So what I did here is that I just changed the 0 of the I controller and then see the system response. And this is another way this is a way to tune PID controller based on your intuition. And if we make very large, what can be happened? So DT is derivation, and the can system on the table. Anyways, so this is it. And then if you learn about another method to design a P to meet this system specification, please come to my office hour, and then I explain a little bit more.